So in this case, first of all, we will see that what all is given to us. So what all is given to us, we see that a length is given of the wire, that is L. Area of cross section of this is also given, that is A. And now it is being suspended from one of the end. So as I have already told you this thing, that from this point, let's say that it is not moving, it is suspended, and it can elongate from this portion, the below one. All right. uh, then it is saying that it is going to stretch because of its own weight. Now, if we are talking about own weight, if we are saying that this wire is going to stretch with the own weight, that's going to be mg. We will discuss about it later on again. So the density is also given, that there is a density d, and Young's modulus of this material is given as y. All right, now let's solve. So what we are doing, we are considering this whole length, that is L, but the elongation will not be L only, like the length is only L. How can be the elongation L only? No, it will not be, of course. Okay, so we are considering that it is going through elongation. And what is that elongation? A very small elongation, let's say dx, a very small change in the length. Okay, now we say that if I'm saying that dx is the small length which is being changed, so we have to take one x. And what is this x? This is just the measurement from the lower end to this portion which is being changed. Okay, we are actually considering these things, right? These are not giving, so we're just considering that there is a small change, and that is of dx. And where is this dx located? This dx is located at x length, or we could say at x distance from the bottom of this length, right? So if some confusion is there, that what is x? X is nothing but just the measurement for this dx. Where is the dx? Dx is from x length of the bottom. We have considered this thing. All right, now what will happen? Now there is some external force which is acting on them, but this external force is because of itself only. And what do I mean by itself? That it is because of the mg, the downward force which is acting. Now let's take this a small portion out of here, like this. Let's say that we are taking this a small portion outside, and this is going through the elongation. So what all thing will be acting? First of all, there will be an upside force also. Why? Two reasons: that every action have a equal and opposite reaction. So there is a downward force, that is mg, so there will be a tension force upward also. So there will be a balance thing, or we could say this is upward forces also acting. Let's say it as f. Because of that there is equilibrium, right? Because of that there is equilibrium. Now this mg, we can change the value for mg. How can we do this? How can we just change these values for mg? Mass is not given anywhere, but we know one thing, that mass, or we could say density, is equals to, acha, in this case I cannot represent density with rho, instead I can represent it with d. So let's say density is equals to mass upon volume. This is what we know. Density is given to us d, and volume isn't given, but length is given as well as the area is given. Now, so let's say what will be mass? Mass will be equals to density multiplied by the volume. Density is going to be d only because it is given, but what about the volume? Volume we can write as area multiply by the length. But length, I cannot take this whole complete L length. Instead of that, I have to take a small this distance, right? This length, which is from the bottom to that portion, and that will be equals to x. So that will be x. So if I replace this mass value over here with mg, I can write this mg as dax, dax, and g as well. So DAXG is the force which is acting downward. And because of that, there is some F force also, which is acting upward, in the upward direction, so that there is an equilibrium which is being maintained, right? Now let's come to the formulas which we know. We know one thing, that is stress is equals to force upon area. This is what we know. We have studied this. Now, if I talk about force in this case, then what is the value for force? As I have already told you, that this force, we can say that it is equals to daxg upon a. So you can write what is the value for stress then. A get cancelled out, so it will be dxg. Now what do we do further? We have this value as density multiplied with this distance, which is from the lower end, that is x, and g. Okay, Now in this question we need to find that what is the strain energy, right? So in that case, how will we find this strain energy? This is nothing but just the stored energy inside it, so we will use that formula, that is the change in energy. Why I'm using this change in energy? Because still we are using for the small length, right? Then later on we can integrate it to find it for the whole. Right now we are doing for the small length dx only. Now what we are going to do, now what is the formula then? The formula is half multiply by the strain multiply by the volume. Let's replace each and every value. You can see from this whole scenario that we are not aware about the strain perfectly, but we are well aware about the stress. So we can do one thing, that we can replace the value for strain with the stress. How am I going to do that? We know that the Young's modulus is equals to stress upon strain. In that case, what will be the value for strain? Strain will be equals to stress upon the Young's modulus, this, and this value I'm going to replace over here. So I can write it as half. Stress will remain stress only, but the strain will be converted into stress by Young's modulus and then the volume. Let's place these values now. So half is going to stay half only. What about the stress? Stress is dxg, or you can simply write it as like stress square, right? Stress square, if you are writing stress square, then it's going to be dxg and square of it, and in the denominator still there is the Young's modulus. And what about the volume? Volume can be written as a multiplied by the length. Which length over here you are going to talk? In this case you're talking about this small energy of this small material, like this small elongated length. When you're talking about this length, then you will be taking the volume also of this small length only. That's why you're going to use dx only over here. All right, now when you will solve it further, you will get half multiply by a, then d square x square g square upon y with dx. This is what we will be getting. This is the energy or the elastic potential energy stored in the material because of that elongation for the small length, that is dx, or we could say small elongation dx. But what if I want to find the elongation, or we could say, what if I want to find the total elastic potential energy of this L length which was given in the question? Then in that case we simply have to integrate it. Let's integrate it. So on both this, if I'm going to integrate this du, I'm going to put the limit from 0 to length L. In that case I will be writing integration 0 to L half d square g square a upon y and then x square dx. The things which are constant, I'm going to take it out of the integration sign. So the things which is going to be constant as can be written as half, density is going to stay constant, g is going to stay constant, area and the Young's modulus. Then what are we left with? We are left with x square and dx. Now we are going to integrate it. While integrated, a very simple rule is that you are going to write it x n plus 1 upon n plus 1. In this case power of n is 2, so it's going to be 2 plus 1 upon 2 plus 1, or n power 3 upon 3. We are going to replace this value over here, so it's going to be half, then d square g square a upon y, then it's going to be x cube upon 3. Or you could also write the same as, this is going to be 6, so d square g square a, and now you have to put the limit also. I'm sorry, yes, I just forget to put the limits. When you will put the limits, then it will be L cube upon 6 and y, and this will be the value for the elastic potential energy of this whole length of the material. This is how we solve it.